Hi, everybody. We're going to look at sampling distributions now, and we're going to kind of do this in, we're going to divide it up as far as proportions and means. So we're going to talk about sampling distributions, and then we're going to talk about how we use them in inference, and then we're going to talk about how we do talk about sampling distributions in means and how we use those in inference. We're going to do it for proportions and means. So we're going to start out here with the proportions, and you guys can look at another video, a second video, to talk about the sampling distribution of means. So the sampling distribution of proportion. So first of all, the thing how you make one is you take every possible sample from a population of size n. So if I want to do a sampling distribution with a sample size of 20, that means out of our high school, that means that I have to grab every subgroup of 20. That means each student might be part of multiple subgroups. Okay, there are some groups that are going to be all freshmen, some groups that are going to be freshmen and sophomores and juniors, and so. But there's lots of subgroups in our high school. Out of the 500 kids in our high school, so the sampling distribution, then, to get that, I would have to take a sample, calculate the proportion of whatever I'm looking for, so proportion of people who like pizza, and then plot that. So in a sampling distribution, every location in a sampling distribution anywhere along here is a p hat. These are all different p hat values down here. Okay, so p hat is the sample proportion. Okay, these are all the different p hats. Okay, so maybe I've got a sampling distribution. I find out that a lot of my samples had high values or high proportions. That means that maybe my sampling distribution is going to look like this. Maybe my sampling distribution is going to look like this, where each dot in here represents a sample of 20 people and the proportion of those 20 people that liked pizza. Down here, we got some of the samples are going to have not many people in the sample that like pizza. So that's why that's where we got down here. It's not very, there are not many of them. Okay. The middle of this is somewhere here. But what we do know for sure is sitting at the middle of the sampling distribution is the true population parameter. So if 70% of people in our high school like pizza, then at the center of this is going to be 70%, 0.7. Okay, we know that. That's always, as long as there's no bias in the sampling, the center of the sampling distribution is going to be the true population proportion. The shape, because it's a yes or no, if, and we have to be centered at the population proportion. If the population proportion is sitting over here, and it's going to start out kind of being skewed, okay? So if the population proportion is above 50%, there's going to be a lump of data over here. If the population proportion is less than 50%, lump of data here. All right, but what allows us to do lots of things later on, if we get to control the sample size here, it turns out that is if NP and NQ, or 1 minus P, if as NP and N times 1 minus P approaches 10, both approach 10, the distribution becomes more normal. And in fact, when it becomes 10 or greater, the distribution is approximately normal. So it's not the population distribution, it is the sampling distribution. It's approximately normal, and it's going to still be centered at the true population proportion. So at this situation, NP and NQ must be greater than 10. So let's say that my sample was 100 here. I grabbed 100 students. Well, no, I don't like 100 students in our high school, because 100 students in our high school violates the 10% rule, and we're not independent anymore. Let's do 50 students would be okay. 50%, 50 students would be okay. 50 students. So what is true here? Well, NP, so 50 times 0.7 is equal to 35, and 50 times 0.3 is equal to 15. So notice these two numbers add up to 50 because n times the number of probability of success is the number of successes. N times the probability of a failure is the number of failures. So that's why those add up to 50. So now we take a sample. Now, for instance, if I wanted to know if a single person was weird or not, I could ask them, do you like pizza? And they would say, no, I don't like pizza. Are they weird or not? Well, 70% of the people like pizza, so they're kind of weird. But that's the only thing we have if we ask one person. We can only compare it to 70%. Are they like people or are they not like people? Okay, well, no, they're in the 30% minority in that situation. But if we want to talk about, and this is the next slide, so I'm going to pause there. I'm going to get back to this last piece. What does this, now I got this normal piece here. The spread is also part of this because we have to say the shape, center, and spread. All right, the spread of this is a formula. It's the standard deviation of this p hats is equal to the square root of p times 1 minus p over n. Okay, that's what we get for the standard deviation. Now this is the population proportion, and this is the population proportion other half from 1. So 1 minus population proportion over n. We don't know that very often. We don't know that very often. A lot of times we use p hat here and p hat there as just our estimation. All right, so in summary to that, the sampling distribution of a sample proportion, its center is at the population proportion, its shape is approximately normal when NP and NQ are greater than 10, and the standard deviation is the square root of pu times 1 minus p over n. That's the standard deviation. That's how typical. So let's interpret that. Typically, the proportion of a sample, let's just calculate. Square root of 0.7 times 0.3 over 50. So that is about, well, let's just do it quick. Hit the calculator button and wait for it. So 0.7 times 0.3, enter, divided by 50, enter, and then take the square root. You guys are probably staring at the square root saying, click it, click it, click it. I don't want to, so I'm going to hit this button, 0.5, enter. So 0.064, so 0.064, so 0.065. Okay, so that means that typically I'm going to take a sample and I can expect, or typically the proportion of people who like pizza in my sample are going to be 6.5% away from the 70%. So I'm not going to be very surprised if I get a 76.5 or anything within 76.5 and 63.5. Okay, I'm not going to be very surprised because typically we expect a lot of the data to live in there. So we like to show those two spots, 0.765 and 0.635. So we always show those at the inflection points. So there's our sampling distribution for this. All right. Get rid of that. All right, so that's our summary there. How are we going to use it? This is where I talked about. If I want to talk about the weirdness of a single observation, I just compare it to this population proportion. Are they in the majority or not? Okay, they don't like pizza. Well, only 30% of people don't like pizza. Or they are left-handed. Well, only 10% of people are left-handed. So that's kind of the only way we can do that using the population distribution. The population distribution of a proportion is just a bar graph with two bars. Okay, This is the distribution of a proportion, population distribution. This is at 0.7, this is at 0.3, and this is like pizza, or this is don't like pizza, and this is like pizza. That's the way that works. Oh, you can't even see what I have there, but it's 2 bars. Okay? If you want to compare the weirdness of this group of 20 or a group of 50, well, now you try to compare it in here. If you got a group of 50, that in that group of 50, the proportion of people who liked pizza was 0.8, you'd say, well, I don't know, that's a little bit weird because it's further away from the center than typical. Okay, if you got it at 90.9, that's really weird. That's out here. If you got it at 0.5, that's way down here. That's really weird. Are those part of the sampling distribution? Do those exist? Yes, a certain proportion are going to exist. Some of those samples, because we're responsible for handling all those samples, some of those samples are going to have 50% or less people that like pizza in them. Okay, so that's why you're in that situation. All right, so later on, we're going to do the same thing for the sampling distribution of a mean. But right now, we're going to go on to how can we use that sampling distribution for inference. So this is popping up here. There are 2 types of inference for a proportion. Okay, the first one's a confidence interval. The second one is a hypothesis test. A confidence interval is when it's still loading here. Okay, when we want to estimate, when we don't know what this is, so that's an unknown value, okay, this is the question mark. So I'm going to do this, question mark. I don't know where the center of the sampling distribution, I don't know what the center of the sampling distribution is. So what I'm going to do is I'm going to take a sample of size, I don't know, 100. Okay, I'm going to take a sample of size 100, so n equals 100. And I'm going to find out in that sample of n is equal to 100, I'm going to figure out what proportion of my sample knew somebody that had cancer. Great. Okay, so, and now let's say that's 80%. Let's say 80% of my sample knew somebody that had cancer. Okay, that's my p hat. Oh, there's a spider. Okay, so we got a p hat of 80%, so 0.8. That's my best guess. Okay, now I'm not going to put 0.8 at the center. I don't know what's at the center. I got a sample that's 0.8. I don't know where that's going to live. Okay, so what I'm going to do is I'm going to make a confidence interval that's going to capture, that's going to have with some certain confidence, is going to capture this middle. So what I'm going to do first is I'm going to use this to calculate the standard deviation of this sampling distribution. The other thing I'm going to do is I'm going to use this to check to see if I can use if this is going to be approximately normal. So what I'm going to do is I'm going to say, okay, well, is NP, that's 0.8 times, or that's 100 times 0.8, is that greater than 10? Yes, it is. Is n times 1 minus p, is 100 times 0.2, is that greater than 10? Yes, it is. So what do I get to put on my graph? Well, now I get to put the fact that it's normal. Okay, that gives me the normal check. All right, then I have to ask myself, did I sample this well? Did I do a simple random sample? I guess until then, okay, I guess I didn't know that was at the middle, but I need to know that I sampled well. Otherwise, I wouldn't get a middle. What is this middle here again? Again, that's P, the true population proportion. I don't know what that value is. Okay, now the next thing is, how spread apart is this? How spread apart is this likely? Well, in order to do that, I'm going to use my population proportion. I know that the distribution, the variation of sampling distribution is the square root of PQ over N, or P times 1 minus P over N. So I'm going to calculate that for my distribution. So let's see. That's going to be the standard deviation of P hat, and my best my best guess here is going to be using the p hat. That's my best guess. Okay, so that's going to be square root of, sorry, you're moving a little bit, square root of 0.8 times 0.2 over 100. So 0.8 times 0.2 is 0.16 divided by 100 square root. So I think if I take, that's going to be over, well, let's do the calculator. I think I know what that value is, but I would hate to do it wrong for you. So again, let's come back to here. What we're trying to do is we're trying to figure out how spread out. We're trying to figure out what this is. Our best guess at the shape and spread of this, not knowing the center. We're trying to find the center. We're trying to nail in the center. Okay, so 0.8 times 0.2 divided by 100, and then raised to the 0.5, or taking the square root. It's 0.04. That's what I thought. Okay, so this is 0.04. Okay, this is 0.04. So that means that this spot right here is P plus 0.04, and this is P minus 0.04. Okay, we know those two locations. Now, we know that inside this value, these two values right here, okay, we know that's about 68% of the data. So if I said, well, maybe 0.8 lives here, and I say, well, that's 0.04, I would need to reach out my wing 0.04, okay? Then I would say that as long as my 0.8 fell within these 68% of values, I would catch P, or actually this 34, because we're on the top side. So if I set it at 0.76 and the low side, and then if I said, well, maybe 0.8 lives over here, so how far up would I have to go? Well, if I had to go up there, that would be 0.84. Okay, 0.84 would be P. So right there, that would be the 68% confidence interval, because I've gone one standard deviation above and one standard deviation below. I know, though, that I can set my confidence as high or as low as I want to. We typically do 95%. So 95%, if I want 95%, I need to go out P plus 1.96 standard deviations. And if I want to get 95%, I have to go P minus 1.96 standard deviations. So now if my 0.8 was out here at the boundary there, how far would I have to go back? Well, I'd have to go back 1.96 standard deviations. So then if I did that, 0.04 times 1.96, that's 0.0784. So I'm going to call that 0.08 just for our purposes. 0.08, this distance would be 0.08. So that means that if by luck, bad luck, but if by bad luck, 0.8 lived right here, I'd have to go back 0.08 or back to 0.72 to make sure I grab the middle. Maybe my 0.8 lives over here. Then I have to go up 0.08 or 1.96 standard deviations to capture that. So this is going to be 0.88. So by doing that, now I can be 95% confident. I can be 95% confident that I'm capturing the true population mean, because my 0.8 can live at 95%, can be any one of these 95% of these dots. And I could still go capture the mean. Or maybe I'm here, I can go still capture the mean. Going out by 0.08, I might not have to go up 0.08, depending on where 0.8 is. But worst case scenario, I'd have to go 0.08 to go grab it. So that's a confidence interval version, okay? So to get the most points, you need to follow panic. So panic was state the parameter in context. We are trying to estimate the number of people, the proportion of people at the high school that know somebody has cancer. A, is your sampling distribution normal? Is it centered at P? And is the standard deviation predictable? So that's sampling, SRS, okay? Then you gotta check the normal, NP, NQ greater than 10. And then you gotta check the independence. Okay? Then you have to name your interval. You got to tell people what you're doing. We're taking one. I think the easiest way to do this, folks, is to do this. One sample. We took one sample interval for P. Okay, one sample interval for P. Then the interval, calculating the actual interval. The thing that you're going to need to do here is you're going to say, okay, I know that P hat plus or minus the Z critical times the square root, times the standard deviation of the P hats. So then I would put my numbers in there. 0.8 plus or minus 1.96 times the square root of 0.8 times 0.2 over 100. I would show that. Here's the formula. There's that. Okay? So then I have to give the confidence. We are 95% confident that the true proportion of people at the high school who know someone who has cancer is between I don't remember what our numbers were. I think it was 72% and 88%. There. Oh, and I ran off the screen there. I was turning down there. Right there. This, I know, guys, I know this is a pain in the neck to I know. I'm a math teacher. I don't like writing either. But you got to stop losing. You can't lose P's, you can't lose E's and turn them into P's. Turn 4s into 3s because we don't want to write it. You can't be, you have to write that kind of stuff out. And it's just decent writing, and it's usually up in the stem of the question. So you want to do that. Make sure you get that done. Okay, so this is getting long, I know, so I'm going to kind of speed. I apologize. Confidence intervals, we did all that. Okay. Now, a one sample z-test for population proportion. Okay, proportions always use z-test because we always have the approximately normal thing going on. Okay, when we do means, it's always t-test because we all know the standard deviation. So the population, so when we do phantoms, and I'm going to let you review what phantoms is in your notes. Okay, this algorithm, it's 3-point scoring when they get to the test. So it's three-step scoring. And every one of these is maybe not in this order, but every one of these parts is in that three-step scoring. So you got to make sure, that's why we've done it, phantoms and panic, to maximize your points on the test. It's always good to write down the formula. What I'm learning is that the formula written down a lot of times will count as a couple different things there to kind of help you out. So this would be a one sample z-test for population proportion. All right. So when do you use that? Well, if you already have a claimed population proportion, you're not trying to estimate it. You're just trying to say, somebody said this, well, 94% of people like cheeseburgers in America. And then you're like, oh, I don't know. People really don't like cheeseburgers around me. So I'm going to test people around me, and I'm going to check to see if my population is 94% or not. So that's kind of, or if my proportion of my population is 94% or not. All right, so that's it there. We'll keep the questions coming, and we'll do some more examples later on and get you some more practice. Good luck.